I'm Gabriella Pangelinan with the Florida Institute of Technology, here to present an analysis of manual and automated skin tone assignments with my co-authors, K.S. Krishnapriya from Valdosta State University, Dr. Michael King from Florida Institute of Technology, and Dr. Kevin Bowyer from University of Notre Dame. Our research is motivated by three questions. How consistent are multiple manual skin tone ratings across observers? What variation exists in manual ratings of the same image? And how do we compare manual and automated skin tone ratings of the same image? Our research is motivated by recent news reports and articles suggesting that dark skin tone causes increased errors in facial recognition. In 2018, the New York Times reported that darker-skinned women experience a huge jump in inaccuracy of facial recognition software. In 2019, the BBC reported that original data sets used in facial recognition research were mostly white and male, and so there are huge error rates by skin type and gender. There are three major schemes that have been used historically for skin tone estimation. The von Luschen scale was developed in the early 1900s in order to classify populations according to racial classification. With this method, opaque glass tiles, 36 in number, were compared to a subject's skin. However, this scale gave inconsistent results across different observers, and usage stopped in the 1950s. In 1975, the Fitzpatrick scale was developed for dermatological research based on skin type response to ultraviolet light. That is, skin types were assigned based on how much individuals tanned or burned in the sun. Traditionally, Fitzpatrick ratings have been assigned in person by a trained practitioner. In the late 1990s, individual typology angle was developed. Individual typology angle allows measurements of skin tone from computer-based images and is calculated using the shown equation. In this study, we used the Morph dataset, which is a collection of mugshot-style images taken in a controlled acquisition environment. The African American male cohort of the Morph dataset contains 36,838 images of 8,850 male subjects. In our study, we used 1,871 images from the center and high similarity tail of the African American male imposter distribution. A high-level overview of our procedure is as follows. First, we color-correct images based on the standard 18% gray background used in the acquisition of the Morph dataset. Then, we assign manual ratings to the full face images. Next, we segment face skin from images in order to assign automated ratings. The color correction step is crucial in standardizing both background and skin tone across images shown to manual and automated raters. We begin with the original image and then segment the foreground and background of the image. Next, we remove the gamma nonlinearity of the image, which is a factor applied to images shown on a computer screen. And we calculate the mean pixel background value of the image with gamma nonlinearity removed. Next, we compute 18% gray color correction factor from the linear image and apply it. Finally, we add back gamma nonlinearity to the image and get our final image. Along the bottom are shown images before and after color correction. Visually, the color correction step makes the background appear to be the 18% gray that we know is the setting of the Morph acquisition, and skin tones appear more realistic. Since the Fitzpatrick scale is traditionally used by trained practitioners and assigned in person, we developed the apparent skin tone scale, which is similarly a 6-tone light to dark scale, which uses exemplar images shown in the image from the IJBC dataset to guide manual raters in their assignment of skin tones. In our procedure, 6 human observers independently viewed and rated the 1,871 images from the Morph dataset. Ultimately, the mean of the rating set was used as a consensus manual rating for each image. Ultimately, our 6 manual raters agreed on an AST rating for 46 images with no difference in tone, 966 images within a 1 skin tone difference, and 1,604 images with. The automated skin tone assignment process followed the workflow shown in the images. First, the face was detected from the image using DLib. Then, with BiCNet, we segmented face skin from the rest of the image, then thresholded on the CBCR color channel, and then used the mean pixel value to calculate the ITA measurement. In order to relate the ITA scale and the AST scale, we mapped consensus manual ratings onto the ITA scale to determine best thresholds for the 6 ITA types. One question that arose in the course of our research was, what is the influence of skin tone on false match rate? That is, do ratings of images or image pairs located in the high similarity tail of the imposter distribution differ significantly from ratings of images from the center? Ultimately, we presented 959 images from the center and 933 from the high similarity tail, with 21 images in common. For both automated ratings and consensus manual ratings, there was little difference in the ratings of images based on location in the imposter distribution. That is, we don't find any clear evidence to support the idea that images with darker skin tone ratings are more frequent in false match pairs. In the image shown, we can see that the manual ratings are much more centered around 4, 5, and 6 values, while the automated ratings are more distributed across 1 to 6. However, center and high similarity tail has little effect on how these ratings are distributed. Then we are interested in comparing how automated ratings and consensus manual ratings compare. As we see in the graph, automated rating and the consensus manual rating agreed on skin tones for 466 images with no difference, 1,379 images within a 1 skin tone difference, and 1,771 images within a 2 skin tone difference. Again, there seems to be a small effect from center versus high similarity tail images. What are the reasons for the variation in automated and manual ratings? Well, manual raters viewed full face images, as shown on the left, while the automated rating system only assigned ratings to the face skin masks. We postulate that humans can consider the context of an image when assigning a skin tone. That is, they can see visible areas of highlight on the face or shadows and consider how a person's pose might affect what their skin type appears to be in an image. The automated rater, however, only has access to the face skin pixels without context, including how lighting affects various regions of the face. In future work, we hope to mitigate this discrepancy by showing only segmented portions of face skin to both manual and automated raters. Ultimately, both manual and automated ratings have their own challenges. In the first set of images, we see misclassifications from the IJB-C dataset. From left to right, the images are labeled with skin tones 1 through 6, although from visual inspection, it seems apparent that these skin tones are almost exactly opposite of what they should be. In the bottom image, we see misclassifications in the DIF dataset. All of these images shown have ITA values that map to the dark skin type, while clearly, upon inspection, they appear to be light. However challenging the problem of skin tone estimation is, it continues to be an important part of biometrics research, and we will continue to work towards finding a good automated solution that can scale ratings across large data sets with accuracy of human raters.